So today we finally get to work on solving a system of equations. Today we're going to work on Cramer's rule. We're going to finally put together a matrix work and solve equations. Now you may look at 2 by 2s and go, why would I not just do elimination or substitution? Absolutely, you can do elimination or substitution. But as you worked with 3 by 3s, you don't want to do elimination or substitution with 3 by 3s or 4 by 4s, etc. Cramer's rule comes in very handy for those. And then eventually we'll get into working with inverses as well to solve 2 by 2s and then 3 by 3s, and then eventually we'll get to our calculator. So to begin with, I'm going to show you again the generic process using our unknown variables. This is going to look like this type of problem. This is what our next problem is going to be. But this is the type of thing we're going to do. We're going to solve a system of equations with x's and y's, figure out what that coordinate point is using matrices. So in this first one here, A, B, C, D, E, and F are all just numbers. Those are some kind of number that's in there. So what we have to do is we have to pull out those constants, those coefficient pieces. So my A matrix is A, B, C, D. Those are the coefficients of my variables, my x's and my y's. Make sure your x's and y's are lined up. Then we're going to now introduce what's called a B matrix, which is the answer matrix. And in this case, it's matrix EF. That's what it equals. So now what I can do is I can use determinants and with Cramer's rule to calculate what x and y are. So in order to do this, I'm going to have to find what the determinant of A is. Again, I can only find the determinant, if you remember, of a square matrix. So when I do the determinant of A, it's my first step. Determinant of A, if you remember, is AD minus BC. You have to have a good understanding of how to calculate the determinant because it will be used in all of these. If you can't find it, you're not going to get the right answer. So now I use that to figure out what x and y is. So my x value is the following situation. It's a fraction. The bottom of the fraction is just the determinant of A, which is, again, just a number. Okay, it's just a single number. And on the top, I'm trying to find x. I'm going to have a 2 by 2 determinant in the top. Since I'm trying to find x, the x coefficients were A and C. So those were my x values, the A and C. So instead of putting A and C in the x column, I'm going to put my answers. E and F is going to go there. So E and F goes in place of the x values. So in that first column is EF. And then my y column is still my y coefficients, B and D. So that's going to give me the x value in my system of equations. So there's x. Then I still have to find y. Y is a fraction again, and it's over the determinant of A, and the importance again of the determinant of A. And on the top is a 2 by 2 determinant. Now, since I'm trying to find y, now the answers are going to go in my y column. So now that E and F from my B matrix goes in my y column, and then my x column is still what the x was, A and C. So now I have to do that 2 by 2 determinant on the top, that 2 by 2 determinant on the top of the y. I take a number, divide it by another number. I get another resulting number. Don't you like how vague I'm being? And it gives me some x, y value. So maybe 3 and 5, 3 comma 5. That's where those two equations cross. A half, 2, whatever the case is. So it's going to give you each of those individual situations. Let's move on to actually solving a regular problem. With numbers, again, it's not going to look quite as ugly along the way. So to begin with, here's our system of equations. 2 lines, I need to find the point at which they cross. So when I go through this problem, I need to figure out, again, that A matrix and that B matrix. Feel free to rewind it back to where it was before so you can kind of see the process that we did before. But my A matrix here is just those coefficients. So my A matrix is 9, 4, 3, 5, 3, negative 5, sorry. And then my B matrix is 6, negative 6, negative 21, because again, that's your answer matrix along the way. So from that information, I now have to set up what my x is, what my y is, find the determinant of A, and then I'll find what that physical coordinate point is as to where they cross fairly quickly. Again, confidence in that 2 by 2 determinant is very important. So to start with, I'm going to find the 2 by 2 determinant of A. So it's 9 times negative 5 minus 4 times 3. So therefore, the determinant of A is negative 57. Not a very nice number. Not at all. But realistically, along the way, things are going to simplify out. My answer is just integers here. So this is not a very difficult problem. The numbers along the way just look kind of scary sometimes. So I have my determinant of a. So now if I want to find my x value, go back to the process. X equals. The determinant of a is on the bottom, and then on the top is a 2 by 2 determinant. So on the bottom is the determinant of a. Hey, that's just negative 57. I calculated that already. On the top, oh, I lost my A and B matrix. So on the top, since I'm trying to find x, in the x column is going to be my answers. So my x column is negative 6, negative 21. My y column is my normal y column, which is 4 and negative 5. That's kind of squished together. Sorry about that. My y, bottom, again, determinant of a. I don't have to write that. We could just write what the number is. Negative 57. And on the top is that 2 by 2 determinant. I'm solving for y. Therefore, in the y column goes those answer pieces. So that's where my negative 6 and negative 21 fall into place. And then in my x column is just my regular x column, 9 and negative 3. Again, those are determinants on the top. So now I just have to do a 2 by 2 determinant. So for the first one, negative 6 times negative 5 minus negative 21 times 4, all over negative 57. So the top there, when I go through the calculation, I get 114 over negative 57. The y, I'll finish that in a minute. The y, when I do its determinant, 9 times negative 21 minus, don't forget the subtraction, 3 times negative 6, all over negative 57. So when I simplify that down on the top, I get negative 171. Big, yes, but kind of nice. Over negative 57. So my x value, when I simplify 114 over negative 57, I get negative 2. When I simplify my y value is positive 3. My answer is the coordinate point negative 2, 3. That is where it crosses, x, y. System of equations, where they intersect. I solved it, so I put it in set notation. That's your answer. That is how to solve a system of two equations using Cramer's rule. Now again, you may go through this going, I don't want to do that. Okay, I understand and I'm okay with that. But are you going to be able to solve a system of three equations with three unknowns? X, Y, and Z? Correct? Because when you did that by hand, quite a few of you made mistakes along the way. And eventually, what happens when I give you a system of four equations with four unknowns? Really? You want to do that by hand? Not really. I don't know if I really would want to do that with Cramer's rule either. But this gives you another option to work through. So if I have a system of three equations with three unknowns, process is identical to a 2 by 2. Exactly the same. Pull out your A matrix, coefficients of your x's, y's, and z's. Your B matrix is your answer matrix. So I go through the process. I have to find the determinant of A. You know how to find the determinant of a 3 by 3. You've already done that. That was in the previous video. If you don't remember, go back, refresh your memory. Time consuming, absolutely. But, I don't know, solving a system of three equations by elimination is pretty time consuming as well. So I'm going to have to find the determinant of A because that's going to go on the bottom of all of these. To find x, it's going to be over the determinant of A. To find y, it's going to be over the determinant of A. To find z, it's going to be over the determinant of A. So that's going to be the bottom of all of your fractions. And then your numerators are going to be 3 by 3 determinants, excuse me. Depends on which variable you're looking for as to where your answer matrix is going to fall. Your answer matrix is that B matrix. When I'm solving for x, it goes in my x column. When I'm solving for y, it goes in my y column. And when I'm solving for z, it goes in my z column. Otherwise, you plug the numbers in accordingly. So I'll put those. And once I have those in, I just fill in my matrix along the way. So in my x matrix, I now have my y column that's left, BEH, and my z column, which is CFI. When I'm solving for my y, I have my x column open, so I do my x's, A, D, G, and I do my z's, CFI. And for z, I have my A column open, A, D, G, and I have my y column open, b, e, h. So in order to solve a system of three equations with three unknowns using Cramer's rule, all you have to calculate is the determinant of a 3 by 3 4 times. Determinant of your regular A matrix, and then these specific matrices as well. Please don't memorize which letter goes where. Know how to put which one where. That's the importance of it. So numerically, we're going to go through this. So I have a system of three equations with three unknowns. By hand, we would have grouped two of them together, canceled the same variable, brought those two together, canceled out another variable, figured that one out, substitute, you get your answer. Lots of mistakes with negatives along the way. So in this case, what I have to calculate is what my A matrix is, my B matrix, the determinant of A, and then those numerator 3 by 3 determinants. So my A matrix, I did my B matrix as well right away. Be careful with those negatives. There's no coefficients technically listed for the two y's and then the x and the z. Those, remember, are just ones. 1 times y is just y. So now I set up my equations to find what x equals, what y equals, and what z equals. The bottom of all of these is the determinant of A. So I need to take that A matrix and find the determinant of it. So it's 2 times 1, negative 6, 1, 1, minus negative 5 times negative 3, negative 6, 1, 1, plus 2 times negative 3, 1, 1, 1. And then I calculate each of those along the way. The determinant of 1, negative 6, 1, 1 is 7, plus 5, and then that 2 by 2 determinant is 3, plus 2, and that 2 by 2 determinant is negative 4, and when I do all of that work, I get 21. So now when I go back, for my x, my y, and my z, the bottoms of all of those is 21. So, I mean, that's really not that much work to calculate a 3 by 3 determinant. You just got to be careful with some of the basic operations that you've been doing for ages. Just tend to sometimes make a couple little mistakes here and there. So be super careful of that. So now I have to go back and now have to do all my numerators. So I'm going to at least get them set up so you can see how they work. These are 3 by 3s because it's a system of three equations with three unknowns. My answer matrix is there. Here's my x's, my y's, and my z's. So plug them in accordingly. And then fill in the rest of your numbers. Go through, do this please on your own, make sure that you're able to do it. And now you have three more 3 by 3 determinants you have to calculate, and then simplify them out. If these don't simplify out nicely, something's probably going wrong along the way. These should come out to be common fractions, and your assessment, just in terms of kind of giving you a heads up if you're on the right track. We're not going to give you the most ugly of problems that these are going to look like. So if you have to do Cramer's rule with a system of three equations and three unknowns, you are going to get numbers like 1 or 2 or 5 or negative 6, maybe a half, some common fractions, but you're not going to get 41 21sts. That should give you an idea that something's probably wrong in that numerator, and you'll know to kind of take a look at that again. Now, in the perfect world, is that the case? No. But we don't need to make you second guess yourself when you're calculating these types of problems. So now you'd go through each of these. When you calculate all of these out, you get each of those for your numerators, which then tells you what the solution to this is. It's coordinate point 3, 0, negative 2 system that we solved, which is why I put set notation then around it. So that's the solution to this system. I should be able to plug that coordinate point in for x, y, and z and get a true statement out for all of them. When we solved systems, we sometimes had no solutions that took place. They didn't cross. You may get that as well here. And you should be able to think about why that's going to occur, what that should look like, both two-dimensionally and three-dimensionally. You will know if there is no solution based on the type of solution you are going to get.